In this video, I'm going to talk about differentially private hypothesis testing. I'm going to focus on identity testing, and for the closeness testing part, please refer to our paper. Every day, there is an amazing amount of data being generated. For a specific task, we can assume that the data come from an unknown statistical source. Given the data, we want to infer some properties of the underlying distribution. One of the quintessential problems asked in statistics and machine learning is that, does the distribution satisfy a postulated hypothesis or not? We may face some modern challenges for this task. For example, the number of samples may be small compared to the domain for the following reasons, and we need to protect each individual's privacy when performing our analyzing algorithm. This can be modeled as the following identity testing problem. Suppose you have a discrete set of size k, and a given distribution over the set. After that, you generate n independent samples from an unknown distribution p. With this, your goal is to come up with a tester, which is a randomized algorithm that outputs 0 or 1, which satisfies the following. With probability at least 2/3, if your data is generated from the distribution Q, then you should output 1. If the data is generated from a distribution P that is TV distance alpha far away from Q, you should output 0. The sample complexity of this problem is defined as the least number of samples any estimator should use. Without privacy constraints, this is known to be root k over alpha squared. The privacy notion we are going to use is differential privacy, which is one of the most well-known privacy notions currently. What it requires, roughly speaking, is that if you only change one of the input data points, then the output probability of any output set shouldn't increase by a factor of e to the epsilon. If we further impose epsilon differential privacy on the algorithms you use to do identity testing, this problem has been studied by Cai et al. In 2017, and they gave the following upper bound. In our work, we show that their upper bound is not tight. As a result, we gave the following upper bound, and the extra penalty imposed by privacy is the max of these three terms. One of the terms will dominate in each of these three cases. We also proved a lower bound which matches the upper bound, which showed that our algorithm is information theoretically optimal. The upper bound is obtained by privatizing the statistic used by Diacono-Nicolas et al., which is sample optimal in the non-private case. To prove the lower bound, we give the following coupling lemma. It states that if there is a coupling between two distributions with small expected Hamming distance, then there couldn't exist a differentially private algorithm that could test between them. Then we use Lee-Camp's two-point method, and the hard part is to construct two hypotheses and the coupling between them with a small expected Hamming distance. After that, the lower bound will follow from the lemma. Our paper is available on arXiv, and these are the references. Thanks for listening.